In this lesson, we're going to talk about transformations, and we're going to go into considerable detail about the theory behind the transformations and why the mapping formula that we arrive at works. For a lot of students, they're not so interested in the theory behind the transformations as they are in how to apply them. So the end of this slideshow will contain a bunch of red slides that will contain the need to know information. So if you're someone who isn't too concerned with the theory, you might just fast forward to the end of this slideshow. A transformation is a change. In this course, we will graph complicated curves by referring back to the parent function and then applying transformations, i.e. changes, to them. The process is the same regardless of the parent function relevant to a given situation. During this presentation, we will refer to the function at the right as f, and we will ultimately develop a formula for graphing the function y equals af of k x minus d plus c. Notice that on this function f are the points 0, 0, 2, 2, and 4, 6. We're going to be applying transformations to those three key points. The function on the right is our parent function, and it is not one of the functions that we have previously learned, and it won't be relevant to any work in the future. It's just an otherwise insignificant function with the key points 0, 0, 2, 2, and 4, 6. Now, when we write f of x, the input of the function f is x. So for example, when we write y equals 6f of 3a plus 5 minus 1, the input of the function is 3a plus 5. It's the part in the bracket next to the f. In casual terms, the input is the expression in the brackets to the right of the letter representing the function. Ultimately, as we seek to graph the function y equals af of k x minus d plus c, we'll remember that the function is f and the input is k bracket x minus d plus c. This is the portion in the bracket next to the f. This is sometimes also called the argument. You can call it the input of the function or the argument. The value of a. What does a do? Well, let's graph the curve y equals 2f of x. We know points on the function f of x are 0, 0, 2, 2, and 4, 6. Well, if we make another column 2f of x, we'll multiply all the values in the f of x column by 2. Then what we can do is remember that we're graphing the function that contains the points going through x to f of x, because we're literally saying that y equals 2f of x. So we can get rid of that middle column and just graph a function with the points 0, 0, 2, 4, and 4, 12. Well, that looks like that function right there. The red function is a vertical stretch of the blue function, the parent. We multiply every y coordinate on y equals f of x, the blue function, by the given a value of 2 to result in y equals af of x, the transformed red function. Therefore, the factor is 2. The factor, that's a big word there. That's a very important word. The word factor in mathematics refers to that by which we multiply. So we say that the transformation is a vertical stretch by a factor of 2 because we multiplied every y coordinate, the vertical coordinate, we multiplied every one of them by 2. Vertical stretch by a factor multiply of 2. Let's talk about vertical compressions. Let's say we want to graph the curve y equals 1/2 f of x. Well, we can determine points on the parent function, and as we discussed earlier, these are those points. Now, if we want to know what 1/2 f of x equals, we just multiply that middle column, every entry, by 1/2. And then we can get rid of the middle column because we're just trying to graph the function that goes through the points x 1/2 f of x. How do we know that? Because we're literally saying y equals 1/2 f of x. So when we plot those points on a curve, we get the red function shown here. Now, if you look at that, that's not a vertical stretch. The red function, we didn't vertically stretch the blue one. What we did is we actually vertically compressed it. So we multiplied every y-coordinate on the blue parent function by the given a value of 1/2 to result in y equals AF of x. So what we say is that the transformation is a vertical compression by a factor of 1/2. Again, the word factor means that by which we multiplied. Vertical meaning y-coordinate, so we multiplied every y-coordinate by 1/2. Now what if we have a reflection in the x-axis? Suppose we want to graph the curve y equals negative f of x. Well, we've got x and f of x as shown right there. Well, negative f of x is pretty easy to determine. We just multiply every one of those values in the middle column by -1. And then we can get rid of that middle column because we're trying to graph the function going through the points x negative f of x. And we plot a function that goes through the points 0, 0, 2, -2, and 4, -6. But we also plot the original blue parent function so we get an idea of what the transformation is. And as we can see, what we did is we reflected down. But it's not sufficient to say reflected down or vertical reflection. What we want to do is we want to tell you exactly what the horizontal mirror is, and then you'll know exactly how to enforce the vertical reflection. See, anytime you reflect something vertically, the mirror was horizontal. And anytime you reflect something horizontally, the mirror was vertical. So to be very precise, you can just tell the reader what the mirror is, in this case the x-axis. The reader knows that that x-axis is horizontal and therefore knows that the reflection will be vertical. So the proper way of writing that is reflection in the x-axis. To say vertical reflection is not accurate enough because while you're telling the person that the mirror is horizontal, we don't know which horizontal line that is. It could be the x-axis, it could be the line y equals 1, we have no idea. So the way it's written, circled in red, is the most specific way. So a summary of the impact of the a value is as follows. If a is greater than 1, there's a vertical stretch by a factor of a. If 0 is less than a less than 1, in other words, a is a positive number less than 1, there's a vertical compression by a factor of a. If a equals 1, there's no change, meaning there's no transformation. And if a is less than 0, then there's a reflection in the x-axis. Now, it's possible for there to be a reflection in the x-axis and a vertical compression or stretch. For example, if a equals -2, then there is a reflection in the x-axis and a vertical stretch by a factor of 2. Since the magnitude of the a value is greater than 1, there is a stretch, and the factor by which we are stretching is the magnitude of the a value. We don't put a negative value in the verbal description because actually we accounted for the negative value in the verbal description when we said that there was a reflection in the x-axis. The value of k. Let's graph the curve y equals f of 2x. To show the impact of putting the 2 there, we can begin by starting with half the original x values. So you might remember on the parent function, the x values that we were using were 0, 2, and 4. Well, now we're going to let x be 0, 1, and 2. But then that's going to let 2x be 0, 2, and 4. Then we're going to figure out what's f at 2x. Well, we know what f at 0 is. F at 0 is 0, because the point 0, 0 is on the curve. F at 2 is 2, because the point 2, 2 is on the curve. And f at 4 is 6, because the point 4, 6 is on the curve. Now, what we want to do is get rid of that middle column. And because we're plotting the points x, f at 2x. So what we're going to do is we're going to plot the function that goes through the points 0, 0, 1, 2, and 2, 6. But we're going to plot it right next to the function that goes through the points 0, 0, 2, 2, and 4, 6. When we do that, we get a function as shown in red. What we've done is we've compressed the blue function into the y-axis. We've compressed it. We didn't stretch it. It would be wrong for us to say we stretched it horizontally. We did not. We compressed it horizontally. And what is the factor? Well, when we say compressed horizontally, we're talking about x coordinates because x coordinates are horizontal coordinates. And so when we say the factor, we're going to say, what did we multiply every x coordinate by? So keep that in mind while we have this brief discussion. The red function is a horizontal compression of the blue function. In order to get a value of 2 to be inputted to the function, we need to let x equal 1. Similarly, in order to get a value of 4 to be inputted to the function, we need to let x equal 2. In other words, what we're actually doing is we're multiplying every x coordinate by a half. So the factor, multiplying every x coordinate by a half, that means the factor is 1/2 on those x coordinates. Those x coordinates are horizontal. When you multiply something by a half, you compress it. So we say that we had a horizontal, look at what's written in yellow at the bottom of that slide. We had a horizontal compression by a factor of a half when the k value was 2. Now, let's go back just for a sec. Go back one slide. Multiplying by a half is the same as dividing by 2. In other words, we divided every x coordinate of y equals f of x, the blue function, by the given k value of 2 to achieve y equals f of kx, the transformed red function. The word factor refers to that we are multiplying by. When k equals 2, we're dividing x coordinates by 2. This is the same as multiplying by a half. Therefore, the factor is a half. When we multiply x coordinates by a magnitude of a half, we compress them, make the magnitude smaller. Therefore, as highlighted, when k equals 2, there's a horizontal compression by a factor of a half. Let's talk about horizontal stretches. What if we graph the curve y equals f of 1/2 x? Well, to show the impact of putting the 1/2 there, we can begin by starting with 2 times the original x values. So let's let x be 0, 4, and 8. That would mean half x is 0, 2, and 4. F at 1/2 x would therefore be f at 0, which is 0 because the point 0, 0 is on f of x. F of 1/2 x would, in the second row, be f at 2, which is 2 because we know that 2, 2 is on the curve y equals f of x. And finally, if x is 8, f of 1/2 x is the same as f at 4, which we know is 6. So in other words, the values in the last column are going to be 0, 2, and 6. But remember, we don't need that middle row because we're trying to graph x comma f of half x, because we're literally saying y equals f of half x. So we get rid of the middle column and we graph the curve. So when the k value is a half, notice that what happened is we stretched out horizontally. We got bigger horizontally. Well, what was the factor? Well, let's talk about that. The red function is a horizontal stretch of the blue function. In order to get a value of 2 to be inputted to the function, we needed to let x equal 4. Similarly, in order to get a value of 4 to be inputted to the function, we needed to let x equal 8. In other words, we're multiplying every x coordinate by 2. Multiplying by 2 is the same as dividing by a half. In other words, we divided the x coordinate of every point on y equals f of x, which is the blue function, by the given k value of a half to achieve the graph of y equals f of kx, which is the transformed red function. The word factor, though, doesn't apply to what you divided by, it applies to what you multiplied by. So when k is a half, we are dividing x coordinates by a half, which means we are multiplying them by 2. Therefore, the factor is 2. And when your factor is 2, multiplying by 2, things get bigger. Horizontal stretch. Horizontal because it's the x coordinate, stretch because they're getting bigger. So like the middle paragraph says, when we multiply x coordinates by a magnitude of 2, we stretch them, make the magnitudes bigger. Therefore, when k equals a half, there's a horizontal stretch by a factor of 2. And how about reflections in the y-axis? Well, we don't say horizontal reflection. We instead, as discussed earlier, we state what the vertical mirror is. And when we state what the vertical mirror is, we are able to give the specific horizontal reflection that occurs. Now, f at negative x is the same as f at negative 1x, so to show the impact of putting the negative 1 there, we'll begin by starting with the negatives of the original x values. The original x values were 0, 2, and 4, so let's let x be 0, negative 2, and negative 4, thereby letting negative x be 0, 2, and 4, the numbers we're used to. That makes f at negative x 0, 2, and 6. Then we remember that we're graphing the function connecting x and f at negative x, so we get rid of the middle column, and we plot the points 0, 0, negative 2, 2, and negative 4, 6, and draw a function going through those points. Well, if you look at the blue function, which is the parent function, and the red function, you'll see the red function is just a reflection of the blue function in the y-axis. And so as it says here, we divided every x coordinate of y equals f of x, the blue function, by the k value of negative 1 to result in y equals f of kx, the transformed red function. The transformation is a reflection in the y-axis. And like I said a couple times, there's no need to say that it is a horizontal reflection or reflection to the left. The most accurate way to describe a reflection is to state the mirror in which the reflection is happening. When the mirror is vertical, such as the y-axis, then the reflection is horizontal. So a summary of y equals f of kx would be that when k is greater than 1, there's a horizontal compression by a factor of 1 over k. When k is a number in between 0 and 1, then there's a horizontal stretch by a factor of 1 over k. If k equals 1, there's no change, no transformation. And if k is less than 0, there's a reflection in the y-axis. As it says at the bottom, it's possible for there to be a reflection in the y-axis and a horizontal compression or stretch. So for example, if k is negative 2, then there's a reflection in the y-axis and a horizontal compression by a factor of a half. Since the magnitude of the k value is greater than 1, then we are dividing by a magnitude greater than 1, meaning we're multiplying by a value magnitude less than 1, meaning there's a compression, and the factor by which we are compressing is the magnitude of the reciprocal of the k value. We don't put a negative value in the verbal description. Now, how about the value of d? How are we going to graph y equals f of x minus d? Just a quick little aside. Note that when discussing the value of d, we change the sign in the bracket. This is similar to what we did in grade 10. Remember in grade 10 when we were discussing the curve y equals x minus 3 quantity squared plus 5, we changed the sign of the value in the bracket to say the vertex was 3, 5. Well, let's discuss that a little bit in more detail. Let's graph the curve y equals f of x minus 1. Well, to show the impact of putting x minus 1 there, we can begin by starting with values of x 1 greater than the original x value. So let's say we let x be 1, 3, and 5. That makes x minus 1 be 0, 2, and 4. That makes f of x minus 1 be 0, 2, and 6. But we're being asked to graph the curve going through x, comma, f of x minus 1, so we get rid of the column that just says x minus 1 and keep the column that says x and the column that says f of x minus 1. Keep the column that says x and keep the column that says f of x minus 1. Okay, so we want to graph a curve that goes through the points 1, 0, 3, 2, and 5, 6. Well, if we do that, it's the red curve shown. So what we've really done is we've taken that parent blue function and just moved it over one spot. Now, we're not going to use the word shift or move because we have a very specific word for exactly this type of transformation. That word is translate. So in order to, the red function is a horizontal translation of the blue function. In order to get a value of 0 to be inputted to the function, we need to let x equal 1. In order to get a value of 2 to be inputted to the function, we need to let x equal 3. In other words, we're adding 1 to every x coordinate. Therefore, we add the given d value of 1 to every x coordinate of y equals f of x, the blue function, to achieve y equals f of x minus 1, the transformed red function. And like it says, remember the sign of d is the opposite of the sign that's in the bracket. When d is greater than 0, i.e. when there's a minus sign in the bracket, we perform a translation d units to the right. But what if we translate to the left? Well, pretty straightforward. To show the impact of putting the x plus 1 there, we can begin by starting with values of x1 less than the original x values. So we can let x be negative 1, 1, and 3, making x plus 1 be 0, 2, and 4, making f of x plus 1 be 0, 2, and 6. We're graphing f of x plus 1, which means we can get rid of the middle column entirely. So we're just going to get rid of this column here. And now we're going to plot the points negative 1, 0, 1, 2, and 3, 6, and graph the curve. Well, that red curve is just like the blue curve, only it's been translated 1 unit to the left. So the red function's a horizontal translation of the blue function. In order to get a value of 0 to be inputted to the function, we need to let x equal negative 1. Similarly, in order to get a value of 2 to be inputted to the function, we need to let x equal 1. In other words, we're subtracting 1 from every x coordinate. Therefore, we add the given d value of negative 1 to every x coordinate of y equals f of x, the blue function, to achieve y equals f of x minus 1, the transformed red function. And again, reminder, the sign of d is the opposite of the sign that's in the bracket. So what that means is when d is less than 0, we perform a translation to the left. So how about a summary of y equals f of x minus d? Here it is. If xy is on the graph of the function y equals f of x, then the point x plus d comma y is on the graph of the function y equals f of x minus d. Remember to change the sign in front of the d. The effect is a horizontal translation in the same amount as the magnitude of d. If d is positive, the translation's to the right. If d is negative, the translation's to the left. If d equals 0, there's no translation. And perhaps the easiest one, perhaps, is the value of c. When discussing the value of c, we don't change the sign in front of c. So if we wanted to graph the curve y equals f of x plus 1, this would be perhaps the most straightforward transformation. We can let x be 0, 2, and 4, making f of x be 0, 2, and 6, making f of x plus 1 be 1, 3, and 7. We're graphing the function that goes through the points x comma f of x plus 1. So we get rid of that middle column and plot the points 0, 1, 2, 3, and 4, 7. Then we compare it to the function going through 0, 0, 2, 2, and 4, 6. And we see that the red function is a vertical translation up of the blue function. We add 1, the c value, to every y coordinate on y equals f of x, the blue function, to result in y equals f of x plus c, the transformed red function. When c is positive, there's a translation up c units. But what if c is negative? Well, I think you maybe can guess it. The x column could be 0, 2, and 4, making the f of x column be 0, 2, and 6. F of x minus 1 would therefore be negative 1, 1, and 5. We're plotting the points that go through x and f of x minus 1, so we get rid of that middle column. And there we go. We've got the blue parent function, and the red transformed function is 1 unit translated down. So the red function is a vertical translation down of the blue function. We add negative 1, the c value, to every y coordinate on y equals f of x, the blue function, to result in y equals f of x plus c, the transformed red function. When c is negative, there's a translation down. So a summary of y equals f of x plus c. If xy is on the graph of the function y equals f of x, then the point x comma y plus c is on the graph of the function y equals f of x plus c. The effect is a vertical translation in the same amount as the magnitude of c. If c is positive, the translation is up. If c is negative, the translation is down. If c equals 0, there's no translation. So putting it all together, let's get to the red slides. Here we go. If xy is on the curve y equals f of x, then x over k plus d comma ay plus c is on the curve y equals af of kx minus d plus c. We call this the mapping formula, and we've been establishing it step by step throughout this slideshow. Recall from one of the early slides of this presentation that the input of that function is k bracket x minus d. Make sure you factor k in the input of the function if it's not already done for you. Now, how about the value of a? Here's your need to know. If a is greater than 1, there's a vertical stretch by a factor of a. If a is between 0 and 1, there's a vertical compression by a factor of a. If a equals 1, there's no transformation. If a is less than 0, in other words, it's negative, then there's a reflection in the x-axis, but there might also, in addition to that, be a vertical stretch or vertical compression, depending on the magnitude of a. if you're stating these transformations, you make sure not to state that the additional vertical stretch factor or vertical compression factor is negative. You state that there's a reflection in the x-axis, and then you refer to the magnitude of A when then also stating the vertical compression or vertical stretch factor. The value of K. If K is greater than 1, there's a horizontal compression by a factor of 1 over K. If 0 is less than K less than 1, in other words, K is between 0 and 1, then the horizontal stretch factor is by a factor of 1 over K. If K equals 1, there's no transformation. Now, if K is negative, there's going to be a reflection in the y-axis, and there might also be a horizontal compression or a horizontal stretch. It's possible. And what you do if there is, you state you state the fact that there's a reflection in the y-axis, and then in terms of your verbal statement of transformations, you then refer only to the magnitude of K when stating the other translation, which could be a vertical compression by a factor of, a horizontal compression by a factor of the magnitude of 1 over K, or a horizontal stretch by a factor of the magnitude of 1 over K. Now the value of D. Remember that to determine the value of D, you need to make sure K is factored out in the input of the function, and make sure you change the sign in the bracket. If D is greater than 0, there's a translation right. If D is less than 0, there's a translation left. And then we talk about the value of C. If C is greater than 0, there's a translation up, and if C is less than 0, there's a translation down. Default settings. The default settings of A and K are 1. In other words, if A or K are not apparent, not visible, then their assigned value is 1. Why is that? Well, in footnote 1, it tells us this is because the operations associated with A and K are multiplying and dividing. The identity in these situations, in other words, the number that you can multiply or divide by without changing the value, is 1. That's why the default settings for A and K are 1. The default settings of C and D are 0. And why is that? Footnote 2. This is because the operations associated with C and D are adding and subtracting. The identity in these situations, i.e. the number that you can add or subtract without changing the value, is 0. And that is the end of your discussion of transformations.